Your brain just became a remote control. Imagine controlling your entire digital world with nothing but your thoughts. No hands, no voice, just pure intention. Scientists have just made this a reality with a microscopic chip that slides between your brain and skull, transforming your thoughts into wireless commands at lightning speed. The promise of this technology comes from its extremely small size, paired with its ability to transmit data at very high speeds. Developed through a collaboration between Columbia University, New York Presbyterian Hospital, and other leading institutions. The device is a brain-computer interface built around a single silicon chip. This chip forms a wireless, high-bandwidth link between the brain and external computers. The system is known as the Biological Interface System to Cortex, or BISC. A groundbreaking study published in Nature Electronics outlines BISC's complete architecture, which includes the chip-based implant, a wearable relay station, and the sophisticated software needed to run the entire platform. Most implantable systems are built around a canister of electronics that occupies enormous volumes of space inside the Bodhi, explains Ken Shepard from Columbia University. Our implant is a single integrated circuit chip that is so thin that it can slide into the space between the brain and the skull. Resting on the brain like a piece of wet tissue paper, think about that for a moment. A piece of technology so thin, it feels like wet tissue paper, yet powerful enough to read and transmit your thoughts wirelessly. Shepard worked closely with Andreas Astolias at Stanford University, whose extensive experience training AI systems on large-scale neural recordings, including those collected with BISC, helped the team analyze how well the implant could decode brain activity. BISC turns the cortical surface into an effective portal, delivering high-bandwidth, minimally invasive read-write communication with AI and external devices. Tolias says its single-chip scalability paves the way for adaptive neuroprosthetics and brain AI interfaces that we could only dream about. Before, Dr. Brett Youngerman from Columbia University served as the project's main clinical collaborator. This high-resolution, data throughput device has the potential to revolutionize the management of neurological conditions, he emphasizes. The key to effective brain-computer interface devices is to maximize the information flow to and from the brain, while making the device as minimally invasive in its surgical implantation as possible. BISC surpasses previous technology on both fronts. What would you do if you could communicate directly with artificial intelligence using only your thoughts? The possibilities are truly mind-blowing. Semiconductor technology has made this possible, allowing the computing power of room-sized computers to now fit in your pocket, Shepard adds. We are now doing the same for medical implantables, allowing complex electronics to exist in the body while taking up almost no space. Brain-computer interfaces function by connecting with the electrical signals used by neurons to communicate. Current medical-grade BC is typically rely on multiple separate microelectronic components, such as amplifiers, data converters, and radio transmitters. These parts must be stored in a relatively large implanted canister, placed either by removing part of the skull or in another part of the body like the chest, with wires extending to the brain. Now imagine having to carry around a bulky device inside your skull or chest, with wires running through your body. Not exactly convenient, right? BISC is built completely differently. The entire system resides on a single complementary metal oxide semiconductor integrated circuit that has been thinned to just 50 micrometers and occupies less than 1/1000th the volume of a standard implant. With a total size of about 3 cubic millimeters, the flexible chip can curve to match the brain's surface perfectly. This tiny device contains an astounding 65,536 electrodes, 1,024 recording channels, and 16,384 stimulation channels. Because the chip is produced using standard semiconductor industry manufacturing methods, it is suitable for large-scale production. Let that sink in. Over 65,000 electrodes in a space smaller than a grain of rice. That's the power of modern semiconductor technology. The chip integrates a radio transceiver, a wireless power circuit, digital control, electronics, power management, data converters, and all the analog components necessary for both recording and stimulation. The external relay station provides power and data, communication through a custom ultra-wideband radio link that reaches 1 megabits per second throughput at least. 100 times higher than any other wireless BCI currently available. Operating as an 802.11 Wi-Fi device, the relay station effectively bridges any computer to the implant seamlessly. BISC incorporates its own instruction set along with a comprehensive software environment, forming a specialized computing system specifically designed for brain interfaces. The high-bandwidth recording demonstrated in this study allows brain signals to be processed by advanced machine learning and deep learning algorithms, which can interpret complex intentions, perceptual experiences, and brain states with unprecedented accuracy by integrating everything on one piece of silicon. We've shown how brain interfaces can become smaller, safer, and dramatically more powerful. Shepherd declares to transition the system into real-world medical use. Shepherd's group partnered with Youngerman from Columbia University. Together, they developed surgical procedures to place the thin implant safely in a preclinical model and confirmed that the device produced stable recordings over extended periods. Here's the exciting part. Short-term intraoperative studies in human patients are already underway. Yes, you heard that right. This technology is already being tested in real human beings, not just in laboratories or on animals. These initial studies give us invaluable data about how the device performs in a real surgical setting, Youngerman explains. The implants can be inserted through a minimally invasive incision in the skull and slid directly onto the surface of the brain in the subdural space. The paper-thin form factor and lack of brain-penetrating electrodes or wires tethering the implant to the skull minimize tissue reactivity and signal degradation over time. Extensive preclinical work in the motor and visual cortices was carried out with Dr. Tolius and Bijan Pesaran from the University of Pennsylvania, both recognized leaders in computational and systems neuroscience. The extreme miniaturization achieved by BISC is very exciting as a platform for new generations of implantable technologies that also interface with the brain using other modalities, such as light and sound. Pesaran notes, can you imagine interfaces that don't just read electrical signals, but also use light and sound to communicate with your brain? The future is getting wild. To move this revolutionary technology closer to practical use, researchers at Columbia and Stanford created Campto, a startup founded by Dr. Nanyu Zheng, one of the project's lead engineers. The company is already producing research-ready versions of the chip and working to secure funding to prepare the system for use in human patients. This is a fundamentally different way of building BCI devices, Zhang emphasizes. BISC has technological capabilities that exceed those of competing devices by many orders of magnitude. As artificial intelligence continues to advance at breakneck speed, BC is gaining momentum both for restoring lost abilities in people with neurological disorders and for potential future applications that enhance normal function through direct brain-to-computer communication. A question for you. If this technology becomes widely available, would you consider getting a brain implant to enhance your cognitive abilities or to communicate more efficiently with AI systems? Leave your thoughts in the comments below. By combining ultra-high resolution neural recording with fully wireless operation and pairing that with advanced decoding and stimulation algorithms, we are moving toward a future where the brain and AI systems can interact seamlessly, not just for research, but for human benefit. Shepherd envisions this could change how we treat brain disorders, how we interface with machines, and ultimately how humans engage with AI. The boundary between biological intelligence and artificial intelligence is becoming thinner than the chip itself. Your brain is about to become the most powerful remote control ever created. Think about the implications for a moment. People with paralysis could walk again. Those who've lost their ability to speak could communicate effortlessly. And perhaps, in the not-so-distant future, all of us could access information, control devices, and interact with AI as naturally as we breathe. What do you think will be the first mainstream application of this technology? Medical treatment, gaming, workplace productivity, or something we haven't even imagined yet? Subscribe to our channel to closely follow the latest breakthroughs in science and technology, and click on the link in the upper right corner to watch our other videos exploring the future of human enhancement.